Hi, Chris Good here. We're going to do another analysis of variance here. This one we're going to do is a repeated measures ANOVA. And this is the example from the slideshow that I posted earlier where we have 5 different subjects and they're going to receive 4 different doses of the drug, including a placebo dose. And we're measuring their behavior. So we're going to see whether there's a difference among these 4 treatment conditions with this ANOVA. And I've given the column totals here for the placebo, drug A, drug B, and drug C. The subject totals, or participant totals here, participant A, B, C, D, E. And we're going to use this to do the ANOVA. Of course, it's a hypothesis testing statistic, so we're going to do all 4 of the steps that we normally do. The first one is to state the null hypothesis. In this case, it's that the mu from the placebo group is equal to the mu from drug A, is equal to the mu from drug B, which is equal to the mu from drug C. Alright? Next step is to state your alpha. We're going to use our old friend 0.05 and to find the critical values for F, but in order to do that we need the degrees of freedom. Now the degrees of freedom are going to be different in repeated measures ANOVA in the numerator, but in the denominator. In the numerator they're going to be the same, right? So that's the between treatments degrees of freedom, which is equal to the number of groups you have minus 1. In this case we have 4 different treatments, placebo, A, B, and C. So that's 4 treatments minus 1, and it equals 3. So in the numerator, we're going to have 3 degrees of freedom. In the denominator, we're going to use DF error. DF error we get by subtraction. It's DF within treatments minus DF between subjects. Not between treatments, between subjects. So DF within treatments we know to be the number of scores you have minus the number of groups you have. Right? DF between subjects is the number of subjects you have minus 1. So if there's 5 different subjects, 4 different conditions, we have an N, I'm just going to write this here for bookkeeping, of 20 scores. Right? I'm going to write down G a little bit later. So 20 scores minus 4 groups minus 5 participants minus 1. That's 20 minus 4 is 16, minus 4 equals 12. So we'll have 12 degrees of freedom for our error term, and we can use that to look up in our F table, and I like to keep a copy of the F table in my Evernote. And if we open that up, let's go ahead and see what the F table is. There it is. So, for 3 degrees of freedom in the numerator, right, and 12 degrees of freedom in the denominator, I get a value of 3.49 for the critical value of F. 3.49 at 3 and 12 degrees of freedom. So you go across the top to look for degrees of freedom in the numerator, right? That's where you go across on the top, and down this column to get to 12 in the denominator. So 3.49 is our critical value. Onward. Then to step 3, which is to calculate F. Well, I'm going to start with F. What do we need for the repeated measures F? Well, you need MS between treatments divided by MS error. Let's go to this first one first. MS between treatments I think we've done before. MS between treatments is the sum of squares between treatments divided by the degrees of freedom between treatments, which we have. That's 3. We just need to get sum of squares. So sum of squares between treatments is equal to the sum of all the squared totals divided by the n for each one of those treatments, minus g squared over big N. G squared I said I was going to write down here. G squared is equal to the sum of all the t's. That's 25 and 20 is 45, 55, 60. So I get 60 for G. And we just do this for each of our t totals. So that's 5 squared, which I'm getting from right here. That's the first t, and you square that, divided by n, which is 5. Next t is 10 for the drug A total. 10 squared, divide that by 5. Next t is for drug B, it's 20. 20 squared, divide that by 5, because there's 5 scores in this condition. The next t is 25. 25 squared, divide that by 5 participants, and that's minus, don't ever forget the second term here, minus g squared, which is 60. 60 squared, over big N, which is 20. Alright, to the calculator then. 5 squared is 25, divided by 5 is 5. 10 squared is 100, divided by 5 is 20. 20 squared is 400, divided by 5 is 80. Let's just double check that. 20 times 20, divided by 5 is 80. And 25 squared is 625. 25 times 25, 625, divided by 5 is 125. 60 squared is 3600, divided by 20 is 180. Okay, so 125 plus 80 is 205, 210, 230. Let's just add these up. 5 and 20 and 80 and 125 is 230 minus 180 equals 50. Alright, so that's our sum of squares between treatments. We can put that in up here. Divide by our degrees of freedom between treatments, 3, and we'll get 16.67. Alright, that's going to be the numerator of our f, 16.67. Now we just need MS error. MS error is, remember, mean square is actually the variance, which is always the sum of squares. So in this case, it's sum of squares error over degrees of freedom. Degrees of freedom for error, right? So where do we get sum of squares error? We get that by subtraction. It's the sum of squares within treatments minus the sum of squares between subjects. Not between treatments. It's sum of squares within treatments minus sum of squares between subjects. Let's do this first one first. Sum of squares within treatments. That's just the sum of all the sums of squares for each group, and I already gave you those here at the bottom. That's 8 plus 8 plus 6 plus 10. That's 16, and 6 is 22, plus 10 is 32. Great. So how do we get SS between subjects? Well, that's the sum of your p totals squared divided by the number of groups that you have. It's as though we're treating these rows as columns, right? And we're treating each participant as a different level of another condition. Of course, this is minus g squared over big N. Let's see how this works. So we do this p squared over k. P for A, that's 20 squared, over k, which is the number of groups, which is 4, right? Plus 12 squared over 4. And for participant C, it's 12 squared again, over 4. For subject D, we've got a total of 8. We'll square that, over 4. Finally, subject E, 8 over 4. We're doing the same thing with the participant totals, the p totals, as we did for the t totals in between treatments. Of course, this is for between subjects, as though the subjects are a form of treatment in themselves. So this is minus g squared, 60 squared, over big N, which is 20, Let's see what we get. So 20 squared, 400 divided by 4 is 100. 12 squared, right, 144 divided by 4 is 36. We do that again, right, because we had that one there. 8 squared is 64, divided by 4 is 16. And then we have one more 16 here. And we remember from above that g squared over n is 180. So minus 180. Don't ever forget this last step here, right? So this step right here. That's very crucial. All right, let's add these up. 100 plus 36 plus 36 plus 16 plus 16 is 204. 204 minus 180 is 24. All right. So that's sum of squares between subjects, but we need sum of squares for error. We're going to get these by subtraction because sum of squares error equals sum of squares within treatments, we got that, minus sum of squares between subjects, and we have that. So that's going to be 32 minus 24, or 8. All right. Now that we have SS error, we can calculate MS error, that's the denominator in our F ratio. So that equals sum of squares error, which we just calculated by subtraction, 8, over degrees of freedom for error, which was 12, right? And 8 divided by 12 is 0.67. Alright, that's MS error. We have MS between treatments. We now have our error term for the F ratio, and we'll see that F 16.67 divided by 0.67 is pretty big value for F of 24.88. Alright, that's our answer. Step 4 is to make our decision. Here's our calculated value of F, 24.88. Here's our observed value of, our calculated value or observed value of 24.88. Here's our critical value of 3.49. The proper decision is to reject the null hypothesis that the treatment has no effect. So remember, with the ANOVA, all you can conclude is that some difference exists somewhere among these 4 groups. So you could say that an analysis of variance revealed a significant effect of drug treatment, but we still don't know what the effect is. And comma, we're still running our sentence, so the F at 3 and 12 degrees of freedom was equal to 24.88. And you know, because you rejected the null, that the P is less than whatever alpha was. And that's it.